Now, other substances can have chirality centers. We've talked just solely about carbon and carbon's ability to have a chirality center. However, any atom that is bound to 4 different groups in a tetrahedron arrangement can be considered a chirality center. And a group can also consist of a lone pair. So lone pairs are counted as a group in its own right if it is a molecule with a lone pair on it. So some of the examples here, you can see things like sulfur or phosphorus can have chiral centers. Here, this phosphorus we're saying is bonded to 4 different things, and that includes a lone pair that is not shown. So this is an S configuration. Silicon can also be bonded to 4 different groups in a tetrahedral arrangement, and so can sulfur as well. This sulfur here is a little bit confusing because it forms a double bond, but it has lone pairs on it as well. So we're calling this bond to the oxygen as one group. It has other groups to its left and right, and lone pair as another group. Now, one atom that you might think would be a great atom to make chiral centers is nitrogen. Now, amines do attach to 3 different groups. They can have 3 different groups attached to them and have a lone pair, which would seem that it would have a chirality center. However, these enantiomers, when you form an enantiomer with nitrogen, so here's an example where we have something A, B, and C bonded to the nitrogen and its lone pair, and here's its mirror image. Now, naturally, if you just took these by themselves and you tried to superimpose them and they stayed as they were, they would be non-superimposable mirror images. However, nitrogen tends to interconvert between these two, and this lone pair actually can move back and forth very easily on an amine. This happens very fast, and because it happens very fast, we cannot technically think of these as enantiomers. They're constantly going between each other. Generally, because of this rapid amine inversion, amines are actually usually drawn as a trigonal planar, which is just their average convert. So we actually just usually draw them like this, just as an average to show where things are connected, and not consider it as a tetrahedral. Enantiomeric amines are better just thought of as conformers rather than any configurational isomer. Now note here that at low temperatures, we can actually stop the movement of this amine from flipping between the two. And so at a very, very low temperature, you would actually see 2 different enantiomeric amines that would exist.